Okay, this is Fall Exam Review Worksheet 4. So number 1 is a similar triangle related rates problem. So for number 1, with the shadow problems, they're all pretty similar. So once you know how to do one, then they're all going to be alike with each other. So we have, it says light on top of a 12-foot pole and 5-foot tall persons walking away from a pole at a rate of 2 feet per second. Okay. So 5 represents the height of the person, 12 is the height of the pole, and I like to set this up with x being one portion of the triangle and y being the second portion of the triangle. Okay. We want to set up a similar triangle proportion ratio. So we can set up using 5. Small height is to the big, the height of the small triangle is to the height of the large triangle, as the base of the small triangle is to the base of the large triangle. So the base of the small triangle is simply going to be y, and then the base of the large triangle is simply going to be x plus y. Okay, so make sure that you don't write your proportion as x over x plus y, because x does not represent the base of any triangle. Okay, x is only a portion of the large triangle. Okay, so if we cross multiply, 5x plus 5y equals 12y, 5x equals 7y. Find the derivative of each term with respect to time. So we get 5 dy dt is equal to 7 dy dt. Okay. The person is walking away from the pole at a rate of 2 feet per second. So dx dt is going to represent the rate of change of the person walking. Okay. Notice that as the person is walking away from the pole, x is getting larger. And because x is getting larger, we want the rate to be a positive. Now the person's walking towards, the lamppost, then x will be decreasing, so therefore we would need a rate of negative. But in this case, walking away, so positive 2. So plug 2 in for dx dt, we get 10 is equal to 7 dy dt. We solve for dy dt, and we get 10 over 7 feet per second. Now dy dt is going to represent the rate of change for the shadow length for that person walking. So rate of shadow length is simply dy dt, and that's what part A is asking for, so it's just 10 over 7 feet per second. Notice that this 25 is never used, and the reason why is if you look at our differential equation, once we find the derivative, x and y drops out, so there's no need for the x value to determine to solve our problem. So this is just a distractor. It's not going to impact our answer at all. So for part B, at what rate is the tip of the shadow moving? So tip of the shadow, rate of change tip of the shadow is simply dx over dt plus dy over dt. So the rate at which the person is walking away, in addition to the rate at which the shadow length is increasing, both rates of changes will affect the tip of the shadow moving. So rate of change of person walking plus rate of change of shadow length, 2 plus 10 over 7. Find a common denominator. We get 14 over 7 plus 10 over 7. That will be 24 over 7. Okay, number 2 is a similar triangle problem involving cones. A tank of water in the shape of cone is leaking water at a constant rate of 2 cubic feet per hour. The base radius of the tank is 5 feet and the height of the tank is 14 feet. At what rate is the depth of water in the tank changing when the depth of water is 6 feet? So let's see what information is provided for us in the problem. Okay, it says that, the tank of water in the shape of cone is leaking water at a constant rate of 2 cubic feet per hour. Okay. Cubic feet, this is talking about volume. Per hour, this is the rate of change for volume. And so we know that 2 is referring to dV dt, and we see that water is leaking out. So we know that water is going to be decreasing over time, and because of that, we know we have to have the rate for dV dt being negative. Okay. The base radius is 5 feet, so we can put that in our have that in our diagram. The height of the tank is 14 feet. I left that out, or got cut off. Okay, so then the water that is in the tank, it will be changing at any moment in time, but we can refer to the radius of the water level as r and the height of the water level as h. Okay, let's see what else. At what rate is the depth of water in the tank changing when the depth of water is 6 feet? So at the moment in time, the height is 6 feet, but we're looking for the rate of change of depth of water. So this is referring to height, but then rate of change, so therefore dH dt. So this gives you a hint as to which variable you want to keep, or that you want to use for volume. Notice if you look at the volume equation for cones, you have two variables. You have r and you have h. So if we want to find the derivative with respect to time as it is, we're going to end up having to go through product rule, and we're going to have to end up with dr dt and dH dt. Now that alone, dr dt is going to be too much information, or rather, we don't have enough information to be able to plug in for dr dt, just based off of what we have. So the reason why we have similar triangles is so that we can replace our equation in terms of the variable that we do have enough information about. Okay, so we can set up similar triangles. Small radius is to big radius as small height is to big height. Okay. We know we have to replace radius, so let's solve for r. Cross multiply, 14r equals 5h. Solve for r is equal to 5 over 14h. Replace 5 over 14h for r. Okay. Distribute the exponent through, so I get 25 over 196h squared. All this is leading coefficients, so I can put all this together, combine the h together, so h cubed. Okay, so here's my volume equation that after I find the derivative, I will have enough information to help me find dH dt. Okay, I'm not going to deal with dr dt. Notice that we don't want to plug 6 in too soon. Okay, the height of the water level is always changing, so we do want to make sure we hold on to this variable until after we find the derivative. Okay, if we plug 6 in too soon into the volume equation, we lose the ability to find the derivative, and therefore we're unable to get to dH dt. So let's now we're ready to find the derivative. Leading coefficient will attach itself to whatever the derivative for h is. So h cubed becomes 3h squared dH dt. V becomes dV dt. We have dV dt is -2. We have height, which is 6. Now the only information that's missing is dH dt. So we can just multiply all this out, divide it to the other side, and that's going to give me -98 over 225 pi feet per hour. Okay, number 3, a function f of x. We're given f of x. What's the instantaneous rate of change when x equals 3? So instantaneous rate of change is simply asking to evaluate the derivative at 3. So we have to go through quotient rule, f prime g minus f g prime all over g squared. Distribute, combine like terms, simplify the numerator, and then I just went ahead and plugged in 3 into the derivative. So I get -28 over 64, so therefore -7 over 16. Okay, number 4, the function f has horizontal tangents at -2, 1, 1, -2, and vertical tangents at -1, 0, and 3, 0. For how many values of x in interval is the function not differentiable? So not differentiable, graphically, what that means is sharp points, endpoints, or vertical tangent lines. So we see that there's going to be, and we're not going to consider these two endpoints because these are outside of our interval. Interval is only between the open interval between -5 and 5, so we don't have to worry about those endpoints. But we see there's a sharp point, so the function is not differentiable at this value here. Another point where we have vertical tangent, and then another x value where there's a jump discontinuity. So we have 3 x values where the function is not differentiable, so therefore answer choice D.